я надеюсь.
Да, слышно.
Хорошо, давайте начинать. Okay, so today's lecture topic is about object detection with convolutional neural networks. So our previous lecture was about semantic segmentation models, where we, instead of just finding what class there is present on the picture, we wanted to map all the pixels into some classes we have. So object detection is another approach for finding objects, where we don't only want to find what classes are present, but we want to locate and create bounding boxes for all the objects that we have on the picture. And as in data set that we used before, like Pascal Walker and MSCO, there are samples of such objects with bounded boxes, so we can use them to train and to predict the bounding boxes with our object detection models. So what are the approaches for object detection? We can start with thinking about object detection task is classifying several objects present on the picture. So for example, if there is only one object on the picture, then we can just use some classification model. And for example, we can add the additional branch in the end that not only predict object class for us, but also it will find the coordinates and dimensions of the bounding box for that object. But if there is not only one object and maybe two objects or three objects, then we need to apply additional classifiers that will find only like the objects in the left side of the picture or the right side of the picture. And for each of the objects, we need to create additional backbone and classifying and bounding box finding branches. And as the number of objects are not determined, this approach will not lead us to success in some arbitrary case. So to find all the objects, we need to somehow to apply our classifiers to all the regions of the image. For example, we can just slide with our classifiers and apply it to some predefined grid of shifts. So for example, we can apply the classifier in the top left corner of the image, then we can slide the appliance, for example, by 8 pixels or 16 pixels and get another prediction and somehow get all the predictions over all the image, but this operation would be very costly. So instead of just applying the classifier to all the regions, we want to somehow just find some region candidates so we can test them and then decide what are the objects to leave as the prediction. So for finding regions, we could use some classical approaches that will not be detailed in this topic, but we can just assume that there are some classic approaches for finding some regions on the image with similar pixel values, with similar texture. For example, on the picture, on the example, we can see that we are finding the bounding boxes regions, the proposals for regions with similar to grayish pixel, to whitish pixels, to pink pixels, and something like this. So we can just assume that we have some predefined method, for example, from OpenCV or some additional library that we can use to find thousands of such region candidates in several seconds. And after that, we can apply our classifying methods, our classifying networks. We can just resize the region candidates on their image to some predefined size, like 200 by 200 for RetinaNet case, and apply our classifier to have the probabilities. And after that, we can just sort all the regions by the probabilities, apply a maximum separation post-processing function, and get all the object present on the image. So this is just exactly the pipeline used in RCNN approach. That is the first convolutional approach to the object detection task. So RCNN is basically regions with CNN features. So we have some input image, we extract regions to try our classifiers with some additional library that takes us just several seconds. And using those proposals, we use the classifier to get the final predictions and classify what the objects are present on this region, if any. Additionally, we can apply some bounding box regression, so we can somehow modify the objects that are present in that region to adjust the bounding box to fit it better for the object that can be found in that bounding box. So the idea is we have several regions, and for each of the region we apply our convolutional neural networks that are quite costly if we apply it hundreds and maybe even thousands of times. So let's imagine that we have some very big object present on the image that takes, let's say, the quarter of all the amount of the pixels on that image. And if we have hundreds and maybe thousands proposals with such big resolution, so if we have maybe just 1,000 proposals that takes approximately one quarter of the image in size, then we need to apply our convolutional neural networks to the images with the quarter of the original size thousands times. What does that mean? If we just take, for example, some first layer and see the convolutions in the first layer, then we apply those convolutions in that network to some predefined region, and then we take another bounding box proposal that overlaps with that region that we applied it to, and then we apply the same convolution again to have some feature maps to apply next convolutions and so on. That means that some initial layers as well as some next layers, they just run over and over the same pixels. They do the same calculations. So the idea is, what if we could store the information for the previous layers, for all the layers of the network? So if we need to calculate our feature maps for the final decision of bounding box regressors and classifiers just once. So we calculate all the needed features of the entire image. So it will take us, so we just run all the convolutions over the image and store it and reuse it in all the region proposals that we have. That would save us reduce the computational time maybe by hundreds of times, because if I have again like one quarter of the image size region proposals, we have hundreds of them. That is approximately the same as we just run the entire convolutional network all over the image hundreds of times. So the idea, we could do the calculations for our features only once and then reuse it for all the region proposals we have. So basically, this is the idea that is lying behind the fast RetinaNet approach. So we speed up our network by optimizing the feature calculations by calculation the features only once. So we have our image, we use so if you have some classifiers previously that we applied to our network, like in VGG or something, we could use only backbone part of the VGG, like we used in semantic segmentation approaches, where VGG had feature layers, and classifying layers. So we take only feature layers and run that feature layer over all the image. And after we run the feature layer of VGG on the image, we have some predefined feature map. And if you have some region proposal on the raw image, then we could map that proposal onto the feature layer. And we could just take that feature layer, resize it some way to the predefined size. So if the original classifier used the 224 by 224 regions to on the original image to classify that region, then we need just 7 by 7 feature map on the region on the feature map to make the final classification. Or maybe in ResNet case, we just need to do the average pooling. So we need to somehow map the region on the image into the feature map. So as we have the some coordinates on the original image, we need to, for example, divide them by 32 in VGG or ResNet case to get the coordinates on the feature map. But as we have some integer type coordinates on the original image, if you divide them by 32, we will get the float number coordinates, but we need to map somehow those float coordinates onto the feature map. So we could basically just round those coordinates to find the coordinates on the underlying feature map. And the next step is, as we found some region on the feature map, they could be arbitrary and in terms of size. For example, we could find the 12 by 15 feature map on the image, but we know that we need 7 by 7 feature map to apply the final layers of our classification for the classification layer. So we need to resize that arbitrary size region, like 12 by 15, resize it into 7 by 7. So one option is to just some resizing with linear interpolation or cubic interpolation or anything. But for the sake of saving the outputs of our network, the outputs, the signal that we got on the previous layers, the ROI pooling layer is introduced in this paper, and we will discuss it later. So basically the idea of faster CNN is to run all the backbone we have only once over the entire image, and after that we have some proposals on the original image that we map onto the feature layer that we get running all the convolution layers of our classification network. Then we apply some magic ROI pooling layer that turns arbitrary sized regions on the feature map into predefined regions like 7 by 7 resolution to be fed into the fully convolutional layers of our network. And then we apply additional classifiers for the final decision for both class predictions and additional linear layer for the bounding box regression to adjust the position of the region, to adjust the bounding box to be pictured on the original image. So what is this ROI pooling layer? The idea is we have some region that we found on the feature map, and let us assume that we have the 2 by 2 input for the final classification layer. So one of the options is just to, so this is the region, this is the entire feature map. One of the options is to just resize all those pixel values that we have in our region found on the feature map to get the 2 by 2 picture. But for example, as we see at this output, so we have 0.96 output for some convolution that we have in our network, and this could say us that there is definitely some object present on that image. So if we have the convolution that would find cats on the image, then we see that there is a cat somewhere there, and maybe somewhere there. But if you just use the interpolation, then we mix this value with the nearest values linear to that pixel. So we will take some mixing and averaging, and then we will lose the information about this pixel value. So we need to somehow somehow save the information that we actually found something. And this is exactly what is done in all the convolutional networks when we apply not just average pooling and some resizing, but we apply max pooling to preserve the signal found on the underlying layers. So let's just um, make some max pooling, but as we need not 7 by 5 region and we need 2 by 2 region, we divide the region that we have on the feature map, not exactly 2 by 2, but approximately 2 by 2. So we make the columns and rows approximately equal one to another, for example, like this. And in each subregion, we just apply max operation. So it's like max pooling, global max pooling, but with some adaptation to not do any resizing. So we apply just maximum to all the subregions and store only maximum outputs from each subregion. So the output would look like this. So the idea again of repooling that we have some original proposal found on the image. We run the convolutional neural networks on the entire image to have the feature map. So we can map the original proposal from the image into the region of the feature map after running the convolutional backbone. Then we divide that region into 7 by 7 subregions. For example, for the VGG and ResNet networks, we need 7 by 7 feature map output for the final classification decision. So we apply the division, we apply the row pooling, so we apply the max pooling operation in all these subregions. Then we have stack of features that can be fed into the fully connected layers. So for example, VDG, or then we can apply just average pooling for the ResNet architecture. Then again, if we apply the array pooling, we haven't done any averaging, we haven't done any resizing. So we just store all the information, all the signals that we had on the previous layers. But if you could apply, for example, not just array pooling, but some averaging, we could lose the details if we do the warping of our region to make it just square, or if we, instead of using the original proposal, we could crop some center to save the information, but we could post it instead of preserving the signal that we haven't found on the underlying layers. So the array pooling operation helps us to save all the signal about the object that we had and to feed that information into the final classification, final decision layers of our network. Okay, so initially we had some proposals. We had very very costly applying of convolutional networks in the first RCNN approach. Then we sped up the feature extraction with faster CNN, so we optimized the feature extraction. But originally we took the classical approach to candidates proposal that took us several seconds, but it didn't matter because all those extraction and running the full convolutional neural networks thousands of times, it costed us more, so we didn't care about the candidates getting the regions for several seconds. But as we sped up the running the convolutions, running the predictions, so now the last bottleneck that is that's still present is the original proposal finding. So we need somehow to speed up that proposal finding too. And that is exactly what is done in faster SNN approach. So we find the last bottleneck left, that is finding the proposals, region proposing that took size several seconds per image. And we want to somehow optimize it. And for that, we use the same network that we used to extract pictures. We used it to find the proposals. So we run the convolutional part of our backbone of our classifier, and we get the feature map. So we want to find some special layers, some special mini networks to find the region proposals. Then we map those proposals on the feature map that we have. And after that, we have the proposals on the feature map to run the classification and bounding box regression part left. So what is the region proposal network? We divide our image in some grid, so with some sliding of the grid, for example, 8 by 8 pixels, and then we have in each grid cell we apply some bounding boxes in some predefined way. We call them anchors. So in some pixels, we have several types of anchors that cover different different regions with different ratios and different sizes as the initial estimation of the bounded box that is present in these pixels with the center as this pixel. And after that, we apply some additional neural network layer to which we apply the additional classification layer that could find us predict the probabilities of the objectness score. So if there is really any object present in this region, and we have additional bounded box regression layer that outputs us the classifications of the bounded box regression of the bounded box coordinates. And we predefine some number of anchor boxes. So typically we have 9 anchor boxes that look like this. So for each center on our feature grid, we have different type of the initial bounding boxes. So we have the 3 types of the scales for those bounding boxes, and we have 3 types for the initial ratios of the object. So we have the square anchor, we have the rectangle, that vertical or horizontal, and we have 3 different scales. So for each pixel on this grid on the feature map, we have 9 predefined initial anchors, and then we apply the additional layers that we have to somehow adjust the bounding boxes and to define the probability that there is actually an object present on that on that bounding box. So that bounding box corresponds to some object on the image. And we have only scores just for it to be some object. So we don't have, as for now, we don't have the probabilities of the real classes. So region proposal network is just to finding that actually any object is present there. So, and if you run this regional proposal network over all the feature map that we have, so as we divided our feature map into some predefined grid, so we have lots and lots of all the anchors for each of the pixels on the grid we have. So when we use some predefined number of ratios, we use some predefined number of anchor scales, and we slide those anchors over the entire image. So if you, for example, have some predefined original number, original image size like 800 by 600, then we divide into 16 by 16 grid. We find we apply all the anchors on all this grid. So in the end, we would have tens of thousands proposals for that image. And we need somehow to filter them if they, for example, correspond to the object that is not actually light into the image. Oh, sorry. Okay, so if we filter out all those anchors, then we would have only some reasonable amount of candidates, like we did in the classical approach when we left only several thousands of the proposals to classify them and filter out them later. And as for the this mini network for the bounding box regression, we need to just somehow learn the transformation of the bounding box proposal into the real bounding box. And for that, we could take the image with our ground truth bounding boxes. We could somehow adjust them randomly, and then we would want to learn the transformation for making the adjusted bounding box, the thrown bounding box, into the ground truth bounding box. And for that, we have some linear transformation that we need to learn. So basically, we have some real bounding box. We have some um, true bounding box, some predicted bounding box. If we want to find the transformation that could make the proposed bounding box closer to the original bounding box, and that could be done with some just linear transformation. And we have the optimization task for classifying, for training that adjust bounding box adjusting layer. So all the original proposed network algorithm looks like this. We have some predefined hyperparameters for creating the anchors all over the image we have. So we calculate all the anchors. We filter on very wrong one after the applying of our transformation network that turns the proposed bounding boxes into more real looking bounding boxes. We sort all the proposals we have, and we filter and leave only several thousands of them, like in the original R-CNN and faster CNN case. Then we remove again all the anchors that are not featured into the image boundaries. We remove some anchors that are too small or too big. Then we apply non-maximum suppression, that is some just predefined approach, classical of there are some even GPU-based non-maximum suppression layers as for now. So basically, we just remove the bounded boxes if they overlap one by another, and they will both have large scores for that object. So we need to leave only one bounding box from the set of intersecting bounding box for the same object. And basically, the region proposal network is what finds the object for us, and after that we need to just apply the classification and bounding box regression layers additional after we leave only some predefined number of detected objects. And to train the faster CNN approach, so we need first to train on the original proposal network, and for that we could use some predefined pre-trained backbone, like we did, for example, in semantic segmentation approaches, where we took the pre-trained backbone, for example, for the UNet, where we took the VGG13, and that had pre-trained weights for the ImageNet. So if we wanted to train the portrait segmentation model, we just used the pre-trained encoder, and basically only the decoder part was trained for that case. So we could take the image classification backbone that is retrained on the ImageNet. Then we could take the ground truth boxes for all the objects that we have in the training for the faster CNN, apply the ImageNet feature layers to extract the features, and train RPN on top of those predefined features for the training. And after that, we could we could use the now trained RPN to extract the proposals for the faster CNN classifier, And we could use again the pre-trained weights for the classification part of the faster CNN to adjust the classification backbone for both training, for both proposing regions and for both the final classification at the same time on the second stage. And on the third stage, as we did adjusted the classifier, we could adjust the RPN by retraining the proposals with not the original pre-trained backbone, but with the adjusted backbone with the classification training part that we have on the previous stage. And basically, we could just repeat this procedure several times. So we could adjust RPN, adjust classification, then use the adjusted classification for fine tuning the RPN, and again. But basically, we could use only several stages to come to some local minimum, local maximum of the quality, and then we could just fine tune all the network into end-to-end style. And if you will try to find some implementations of faster SNN, if you could use the GPU-based non-maximal separation, GPU-based region proposal networks with custom CUDA code for the pooling layer, then basically you could use all the network or the pipeline in end-to-end style. So you could just fine-tune all the network you have. And to compare the speed that we had initially with R-CNN, then we optimized the feature extraction and classification bounded box regression with the extraction of the features for all the image at once. And so we left only with one bottleneck of region proposals. And when we replaced the classical region proposals with our region proposal network, we've come to some really fast speed of the entire approach as faster SNN. So basically, faster SNN is the default approach from the two-stage family. So two-stage approaches are the approaches that we initially find some proposals in some way, then we filter out those proposals, and after that we run our additional network, additional pipeline part to classify all those proposals, to filter out them more, and to make the final decision on the objects that are present on the image. And as we had several architecture approaches in semantic segmentation networks, for example, when we had encoder-decoder approaches or some encoder modification approaches, as well as in the object detection approaches, we had several families, so it was one of them. And for the next object detection approaches family, we will continue in 5 minutes, I think. So let's have a short break as for a while. And if there are questions, you are free to ask. Let's continue. As for now, we've overviewed the R-CNN approaches, R-CNN family approaches, when we had two stages. The first stage was finding the proposals and filtering them out, and on the second stage, we did the final decision on the classification and bounded box regression. So this covers the basics for the two-stage approaches. We will take a look at some new two-stage approaches later, but as for now, let's go with the one-stage approaches that require not any additional region proposals to find the final object on the images. So one of the example is YOLO network that is you look only once. So unlike the two-stage approaches, the idea for one-stage approaches and YOLO in this particular case, so we have some convolutional layers. So for YOLO, it's not some predefined backbone like RetinaNet or something, and just some custom layers, custom convolutional layers. And when we run this network, we end in 7 by 7 region with predefined number of features. And then we apply again the convolutional layers and fully connected layers to leave only 7 by 7 region with some predefined number of classes. And then we use this 7 by 7 grid output to find all the objects that we have on the image, and we don't find any proposals on the original image. So as the output, some preliminary output, we have some predefined grid on the image. Then we have the bounding boxes that are built with this predefined grid, and for each bounding box rectangle that we could find on the image, we calculate the modification for that rectangle, the adjustment, and we find the probability for the objectness, and additionally we find the class probabilities for each grid cell on the on that 7 by 7 output. So, and after that, we could multiply the bounding box that we find on the image with some predefined, pre-calculated class probabilities to get the idea of what the object class for that rectangle region that we found in this branch. And these two probabilities multiplied will output us all the object on the output, and then we could apply the maximum suppression to filter out the some objects and to leave only one bounded box for some real objects on the image. And after that initial YOLO only once approaches, several additional YOLO versions were out. So I think as for now there is only not only three versions, but maybe YOLO v4 is already present out there with some implementations. But as this is quite fast one stage approach with anchors, it wasn't widely used until recent time because the original YOLO implementation was written in C code, not even C++ code. But after that, it had the C++ implementation, and you had to use that implementation to retrain your YOLO network to run the predictions. And for example, if you could just modify the, for example, number of classes for some arbitrary number, the code started to fail. So these approaches were not widely used until some time. So, for example, it's only several years ago when some PyTorch implementations, easy PyTorch implementations, were created for the YOLO, and after that, it sometimes the people started to use this network in their custom solutions, but generally, instead of look only once approach for the one-stage detectors, there is another similar approaches that is SSD or single shot multibox detector. The idea is similar to the YOLO, and that we have some predefined grid on the image, and similar to the faster CNN approaches, as we for each grid on the image we have some predefined number of anchors for each cell on that grid, and for that predefined number of anchors we apply the bounded box regressions, and we use the confidence output for the objectness score. So this is the probability that is actually any object is present with respect to that bounding box of the anchor in that particular location. So the output for each anchor we have five numbers. So the bounding box coordinates, bounding box dimensions, and the confidence, the probability of the object being present there. Then we have the 7x7 grid, and we have different number of base boxes and class outputs. So this is bounded box output for the object that is present, and we have some number of classes. So we have some predefined number of outputs, and then we can filter out the applied and maximum suppression to get the final decision. So again, this is just one stage approach. We run all the network, we have the outputs, we filter them out and get the final decisions for our methods. And as the YOLO approach, SSD could use some custom-made layers, but actually there are some SSD implementations on top of the predefined encoder. So for example, original SSD was built with the VGG encoder, and unlike the YOLO, when we had only features from the last layer to make the final decision on the bounded boxes and classes, the SSD aggregates the outputs from different feature output stages. So when we run the our backbone, after that we apply several custom convolutional layers and we aggregate all the preliminary outputs of those convolutional layers to make the final classifying decision for bounded boxes and classes. And so basically in general cases, SSD is both simpler to implement. It had the various implementations for both TensorFlow and PyTorch and other frameworks. And as it aggregates features over the different resolutions, SSD basically finds, in general, it finds more object and even smaller object compared to the classical YOLO approach. And after that, several adjustments were proposed for both SSD and YOLO. So there are several modifications of SSD approaches as well as different generations of YOLO approaches. For example, YOLO v2 is just the YOLO approaches with all fancy features that were presented in different papers between the YOLO and YOLO v2 papers. But as for now, as I've said, there are already YOLO v3 and YOLO v4 approaches with the more simpler implementations than the original C++ custom code for the original YOLO approach. And to compare the two-stage classical two-stage approaches as faster CNN and more or less classical one-stage approaches as YOLO and SSD, we could see that SSD is somehow compared to the faster CNN quality with the large objects. The difference become larger for the medium and smaller objects. That's because for SSD and YOLO we have some predefined network of anchors. We have predefined cell grid, so we miss some small objects. But for faster CNN, we have some very big and small step-sized grid. So we have thousands of proposals that we could filter out, and thus faster CNN allows us to find both big objects and smaller objects on the images. And as the SSD approach combines features from different feature layers, from different preliminary outputs, it could find more detailed objects compared to the YOLO approach. So basically, SSD is some sweet spot for the large objects. You don't even need some more complex two-stage approaches if the SSD output quality is enough for you. And in general case, it's easier and better to use SSD approaches than YOLO approaches. And another example of one-stage approach that could even beat the two-stage faster CNN model is RetinaNet approaches that is based on the FPN backbone, that is feature pyramid network. It was proposed in different article, so it was not firstly discovered in the RetinaNet. So the idea of FPN that we had initially several approaches to the combining outputs from the different resolutions, from the different feature layers. So one of the classical approach to combine the feature outputs for different sizes of the objects is to create the feature image pyramid when we resize all the image we have into different scales and get the features for the different scales and aggregate the features from different scales to feed into some next layers or anything. So we could combine the uh, features for both small objects, small regions, and big objects, big regions, and etc. So, and originally, if we had just some classification model, we had only a single feature map to make the final decision. And for example, in some encoder decoder semantic segmentation approaches, we use the feature from all the layers to feed into some additional network, some additional decoder, and feature pyramid network idea is not only to aggregate the features from different layers, but to run it in some signet like way to aggregate the not in only in forward way, but in the backward way. So we could apply some predefined convolutions for those feature outputs to have the some predefined number of feature layers in that size. Particular after that, we upscale and combine them with uh, additional preliminary feature layers from the backbone, and then we could apply additional upscaling and so on. And we not only use the last big scaled output to make the final decision, like we did in, for example, UNet, but we additionally store all the outputs and on the decoder stage too. So we not only aggregate all the outputs from the encoder so-called encoder stage, but we both aggregate the feature outputs from all the decoder stage, and then we use them to run the final decisions. So as for RetinaNet, we have some predefined backbone like RetinaNet as the encoder. We run the FPN, so we calculate some convolutions for all those feature maps with some predefined small number of feature layers to have and at the output. And after that, we apply additional subnets for classifying and bounded box regression. So basically, there are some additional convolutional layers. Um, in some ResNet likewise, we have some several ResNet like blocks with convolutions and poolings and residual connections. And then we apply some additional convolutions to make the final decision with some predefined number of anchors. And we have some additional branch for the bounding box regression with some linear layers in the end to make the bounding box adjustments. So, and as we have some predefined number of anchors, this is another one stage approaches, but we also rely on some anchors to find the propositions and to find the fixed number of proposals and then filter them out. And additionally to that structure, RetinaNet paper had another idea. So when we used the fast RetinaNet approach, we had a large amount of proposals that we filtered out later, but we could somehow estimate the precision of the confidence of our predictions to filter out only very confident approaches in the first. So the idea in RetinaNet is to use focal loss. It is the form of loss that is defined by these formulas. That the idea that we diminish the very confident outputs. So we want the network on the training stage to train to get the information from the outputs where it is not very confident. And this allows us to speed up the approach and to leave only to make all the predictions we have quite confident. So even for smaller amount of the proposals, all the proposals would be confident, and on the filtering stage, we have more real object-bounded boxes in the end. And as for the comparison, this one-stage approach with FPN backbone and some additional subnets on top of that, and this training approach with focal loss on the training stage. This RetinaNet paper achieved better or similar performance compared to all the two-stage heavy approaches and both the just SSD, just one-stage approaches too. And there are some charts for what are the parameters for this focal loss function that is parameterized with this gamma and alpha numbers. And as for these parameters, there are some sweet spots found in the paper. And actually, if someone now uses the focal loss, for example, for segmentation, it is very useful when you need to refine the boundaries of your object. And when you have quite confident predictions and not confident only from boundaries, for example, the focal loss could be used in that competition about car segmentation. We've seen in the previous lecture to improve the boundaries, to train the model only to improve the boundaries, as all the other predictions are quite confident already. So this focal loss is mostly used with these default parameters found in the original paper. And when we use focal loss, we don't generally modify that and predefined parameters for the loss of the gamma, and there is another parameters in the original paper. And as I've said, there is another YOLO approaches that they just wanted to leave the only one comparison chart from. So that you could see that in the original paper we had not zero-based charts for the comparison, and YOLO v3 approaches, the authors just left this comparison chart and applied their new qualities on it. But this basically was another approach with additional DLC that were found from all the papers that were out between the YOLO v2 and YOLO v3. But again, the people mostly used and continued to use the SSD and RetinaNet implementation because YOLO implementations were not quite easy to use and to adjust for your custom tasks compared to the SSD and RetinaNet approaches. Okay, so let's basically, we have already overviewed the two-stage approaches for object detection. We have reviewed some of the one-stage approaches to the object detection. And let's take a look as for now for the instant segmentation task. So we had a semantic segmentation theme on the previous lecture, but we hadn't looked at the instant segmentation. So where we want to make the semantic segmentation for each object present on the image. And we didn't overview the instant segmentation in the semantic segmentation lecture because instant segmentation is more about object detection than actual segmentation, because we need to find all the objects at first, and after that we apply semantic segmentation, some small semantic segmentation network for each object that is present, and to find all the instant segmentation maps and all the general approaches, all the well-performing approaches in the papers, they use this scheme. So basically, most of the instant segmentation approaches are basically just object detection approaches with some additional branches, some additional adjustments made for the semantic segmentation tasks for the semantic segmentation for each object that were found. Okay, so basically we could take a look at masked R-CNN approach, and that is based on the faster R-CNN approach. That is the object detection. So masked R-CNN is an instant segmentation approach based on the object detection model faster R-CNN. And the idea is that we again have some predefined convolutional neural network that would find us the proposals on the feature map. Then we apply several um, stages, but instead of Roy pooling, we apply Roy align layer that I will describe later. And when we apply additional final layers for the final decisions, we apply not only the classification, but we apply some small semantic segmentation networks. So we have the branch for classification score and bounded box coordinates, and we have additional layers that are purely convolutional layers that predict the small binary mask for us to apply to the bounded box that we found. And after that, we will have the semantic map for the object that is found in that bounded box. But as I said, instead of Roy pooling, we apply Roy align, and what is it? So when we had the Roy pooling layer, so the idea was that we found some proposal region on the feature map, on the original image that we wanted to map onto the feature map. And as we had some integer coordinates on the original image, the corresponding coordinates on the feature map regions could be real valued or float valued numbers, and we somehow needed to mm, round those numbers to take the real to take the integer coordinates on the feature map, and after that we applied the Roy pooling operation to find the to preserve the maximum outputs, to preserve the signal found on the previous layers, and after that we applied some bounded box regression to find the bounded box for the image. And the thing is that we lost some spatial information for our object to find the precise bounded boxes as we make some roundings for the numbers, for the coordinates. Then we lost some information. So the bounded box could shift maybe or could warp by several pixels. But as for object detection task, that is not very Mm, it's not can be seen easily that the bounding box is shifted by several pixels because as for human eye, it's okay if the bounding box is not covering the exact boundaries of the object, but it's more or less confident and correct, and this is okay. But for semantic segmentation maps, if we have the semantic map for some object and this semantic map is shifted, somehow warped and resized, then we could easily see that there are some pixels out of the object, there are some pixel missed on the object. So we need to adjust the correctness, spatial correctness of our mask prediction to make the overall quality and eye pleasure better for our outputs, for our predictions. So instead of just rounding the float coordinates of our region proposed regions, we store and we leave the float number values. So instead of just mapping the region proposal that we found with float valued coordinates on the feature map, instead of just rounding it, mapping it into some another um, another region on the feature map, we create the value based on the interpolation. So instead of we have this 4x4 proposal that we map into the feature map layer, and instead of just rounding that corners and uh, take the pixel values of the feature map, we create additional 4x4 intermediate feature map values when we have the values in these new cells that were interpolated from the values of the original values on the uh, feature map layer. And so the outputs here and here, they would be based on the outputs we see on the feature map, but we don't need any roundings to make the mask placement incorrect and mask place somehow misaligned or missized compared to the original image. So we apply this row align operation instead of row pooling to improve the quality of positioning the bounding box. And as we apply the mask layer, mask branch after that, so the mask for the object would be positioned better for the object we have, for the objects we have on the image. And as we have the both classification branch and bounding box coordinate branch, and we have some mask segmentation branch, we could apply additional branches, additional small subnetworks to not only make these two tasks, but we, in the same way, we could use additional branches, additional regression branches, additional classification branches to find even more details about our objects. For example, we could do the pose estimation tasks. You could simply just add additional regression layers that would find the relative coordinates relative to the object we found, and to find the coordinates for all the human parts on the image to create the skeleton, to create the pose estimation output. Yeah, so basically the most segmentation approaches are just object detection approaches with some additional layers to create the masks, and also we could use additional branches to solve even more tasks than just finding the masks for the object we found on the with the object detector approach. And on these slides, I just wanted you to take a glance at the new generation object detection approaches. So basically, faster RetinaNet was the maybe one of the last great ideas for the two-stage approaches when we created and optimized all the steps we have to train the faster RetinaNet in end-to-end way. And basically, we could take a look at the faster RetinaNet as some two-stage approaches. When we one stage we have some network finding proposals and classes, then we filter out and make the pooling for the all the features we found for the feature map, and then we have additional branch for the final classification and final bounding box regression after we filtered out all the proposals. So we could elaborate on this approach with creating additional branches and make not only one filtering but several filtering stages. So there is a Cascade R-CNN approach when we had additional final stage branches compared to the original faster R-CNN approach. So we have some just initial bounded boxes found on the image. So we run the second stage in faster R-CNN several times. So we run the filter out the proposals, we run the bounded box regression adjustments and classifying adjustments. Then we run another filtering approach, and again we find the bounded box regression adjustments and so on. So basically we run the faster R-CNN branch several times in some RNN style. So we apply the same network several times to improve the predictions in several stages, and the same can be applied to the mask R-CNN approach. So this one paper is only just for you to have the vibe of the new approaches that are built today based on the additional faster R-CNN ideas. And there are even more elaboration on this approach. For example, maybe the current state-of-the-art approach for the object detection and the largest network object detection that you can find on some nice frameworks for the object detection. There is a hybrid cascade and task cascade approach that is based on the just cascade approaches that elaborate even more. So we could create the additional information branch on top of all the stages that we have, and these additional branches they somehow pass the information from stage to stage to have the additional bounded box, additional decision branches, and somehow it becomes similar to not only a RNN approach but similar to some even LSTM approaches. Then we aggregate information over several steps to make the final decision for our bounded box approaches, for our bounded box outputs and class probabilities. And basically, the hybrid task cascade approaches are the best performing as for now, but basically they all just elaborate on the faster CNN approach that we had earlier. So as for two-stage detectors, you just want to basically know that there were some improvements originally from the RCNN approaches. So we had RCNN, then we created the fast RCNN um, to make the classification and classification of final stage and bounded box regression faster. Then we eliminated the bottleneck with the original proposals in faster RCNN stage, and then we created the instant segmentation approaches based on the object detection approaches. And after that, there are some approaches like Cascade R-CNN hybrid task Cascade R-CNN approaches, and maybe there will come another ones that just elaborate on the faster R-CNN approach that had two stages. So they create more stages for the bounded box refinement, for the classification probabilities refinement, and for improving scores even better. So, and the next part of the lecture would be about another different family. So as for now, we have the overview of two-stage approaches that are basically some RCNN family approaches and some improvements over them, and the ideas of how to make the mask segmentation instance segmentation out of object detection. We have the one-stage approaches like YOLO, SSD, and RetinaNet, but we also have some anchors, some predefined initial bounded boxes to adjust and to find the classes for them, the object score for them, and to filter out them later to have the final decisions. And there are the third family of the object detection methods, that is anchor-free approaches. So when we just find all the objects without any additional initial proposals to adjust them and to find all the objects on the image. But before we come to this last family of the object detection approaches, let's have another break and we'll continue in approximately 15 minutes. So if there are any questions, feel free to ask them, but we'll continue in 10 minutes past 12.